You cannot stop it. Right now, as you listen to this, time is moving. Not because you chose it, not because anything is making it happen in any way you can point to or measure directly. It is simply moving, second by second, moment by moment, carrying you forward whether you want to go or not. You have never experienced a single instant outside of it. Every memory you have was formed inside it. Every plan you have ever made was directed toward a future point within it. Every person you have ever known has been subject to it in exactly the same way you are. Unable to pause it, unable to reverse it, unable to step outside it, even for a moment, and look at it from a distance. Time is the most intimate thing in the universe, and almost nobody has any idea what it actually is. Not in the casual sense of not having thought about it carefully. In the deeper sense, the sense that matters. The physicists who have spent their entire careers studying the fundamental structure of reality. The people who understand quantum mechanics, who have worked through the mathematics of general relativity, who have dedicated decades to trying to build a theory that unifies the physics of the very large with the physics of the very small. Those people, when asked what time actually is at its most fundamental level, give answers that are either deeply incomplete or genuinely disturbing. Some of them say time is not fundamental at all. Some of them say time does not flow, that the sensation of movement from past to future is an illusion generated by the way consciousness processes information, and that past and future exist as equally real as the present in a static four-dimensional structure that simply is. Some of them say time had a beginning, that before the Big Bang, the question of what came earlier is as meaningless as asking what is north of the North Pole, because the dimension in which earlier and later have any meaning did not yet exist. And some of them say that when you push the equations of quantum gravity to their limits, time disappears entirely from the mathematics. That the deepest description of reality we can currently write down does not contain time as a variable at all, and that this is either a profound clue about the nature of the universe or a sign that our theories are incomplete in ways we have not yet resolved. These are not fringe positions. They are not the speculations of people on the margins of physics. They are the considered views of serious scientists working at the frontier of the most rigorous discipline human beings have ever developed. And the fact that they disagree with each other so fundamentally, the fact that time, of all things, remains this contested and this poorly understood at the level of foundations, is one of the most remarkable and underappreciated facts about the current state of human knowledge. We have mapped the genome. We have detected gravitational waves from colliding black holes a billion light years away. We have built machines that can factor large numbers by manipulating the quantum states of individual atoms. We have done things with our understanding of nature that would have seemed like magic to any previous generation of human beings. And we do not know what time is. Not really. Not at the level that would let you stand up in a room full of physicists and say, here it is. Here is the complete and final answer to what time actually is, where it comes from, why it moves in only one direction, and whether it is a fundamental feature of reality or an emergent property of something deeper. And have everyone in the room nod and agree and close their notebooks. That conversation has not happened yet. It may not happen in our lifetimes. If this is the kind of content that pulls you somewhere you did not expect to go, subscribing to The Cosmic Depth takes 2 seconds. And we post new documentaries every few days because what we are going to do in this documentary is go all the way into the problem, not the surface version of it, not the popular science version that tells you time is relative and leaves it there as though relativity were the end of the story rather than the beginning of a much deeper confusion. The real version. The version where the comfortable intuitions dissolve one by one, and you are left sitting with something that is genuinely strange. Start with what you think you know. Time passes. That is the most basic, most universal, most undeniable feature of human experience. You wake up in the morning and time has passed since you fell asleep. You look at a photograph from 10 years ago and time has passed since that moment was captured. You feel the difference between the you of 10 minutes ago and the you of right now. The slight shift in position, in thought, in the configuration of everything. And that difference is time having passed. It seems obvious. It seems like the kind of thing that requires no explanation because the explanation is self-evident. Time passes because that is what time does. It is the background against which everything else happens, the stage on which every event in the universe is performed. Except that physics, when you push it hard enough, does not support that picture. Physics gives you something much stranger. The first hint of how strange comes from a thought experiment that Einstein proposed in 1905. A thought experiment so simple, it sounds like it should not have any implications at all, and so profound that it rewrote our understanding of the universe from the ground up. Imagine two observers, one standing still, one moving at high speed, both of them measuring time with perfect clocks, perfect in every mechanical and physical sense, no friction, no wear, no error of any kind. Clocks that measure time as accurately as it is physically possible to measure it. Einstein's question was simple. Do those two perfect clocks agree? The answer, arrived at not through experiment initially, but through pure mathematical logic applied to the known behavior of light, was no. They do not agree. The moving clock runs slow, not because of any mechanical imperfection, not because of vibration or acceleration or any physical stress on the clock's mechanism, but because time itself, the thing the clock is measuring, passes more slowly for the moving observer than for the stationary one. Time is not the same for everyone. It never has been. We did not notice for most of human history because the effect is only significant at speeds that are a substantial fraction of the speed of light. Speeds that no human body and no human-made vehicle had ever reached until very recently in our history. At the speeds of everyday life, the difference between clocks in different states of motion is so vanishingly small that no instrument available before the 20th century could have measured it. But it is there. It has always been there. And once you understand that it is there, once you really sit with what it means that time passes at different rates for different observers depending on how fast they are moving and how strong a gravitational field they are in. The comfortable picture of time as a universal background, a single clock ticking the same seconds for everyone everywhere, dissolves completely. And what replaces it is stranger than anything the comfortable picture ever suggested. In 1971, two physicists named Joseph Haffel and Richard Keating did something that should not have been possible with the technology of their time. They bought seats on commercial aircraft, not for themselves alone, for atomic clocks, extraordinarily precise instruments, the most accurate timekeeping devices that existed in 1971, loaded onto passenger jets, and flown around the world, eastward on one journey, westward on another. While identical atomic clocks sat on the ground at the United States Naval Observatory in Washington and ticked quietly through the same period. When the flying clocks came home and were compared to the ground clocks, they did not agree. The differences were tiny, measured in nanoseconds, billionths of a second, but they were real, measurable, exactly consistent with the predictions of Einstein's theories of special and general relativity applied to the specific velocities and altitudes of the flights. The clocks that had been moving through the air at aircraft speeds, at aircraft altitudes, had measured a slightly different amount of time than the clocks that had stayed on the ground. Not because anything was wrong with them, because time had actually passed differently for them. This was not a theoretical result. It was not a mathematical prediction sitting untested in a physics paper. It was two physicists with atomic clocks on aeroplanes demonstrating that the universe works the way Einstein said it worked. That time is not a fixed universal quantity ticking the same seconds for every observer simultaneously, but a flexible, observer-dependent dimension that stretches and compresses depending on velocity and gravity in ways that are precisely calculable and experimentally verified. And this was only the beginning of how strange it gets. Special relativity, Einstein's 1905 theory, deals with observers moving at constant velocities relative to each other. It tells you that a moving clock runs slow compared to a stationary one, and that this effect becomes more dramatic as the velocity increases. At 10% of the speed of light, the effect is small but measurable. At 90% of the speed of light, a moving clock runs at roughly half the rate of a stationary one. At 99% of the speed of light, the moving clock is running at about 1/7 of the stationary rate. At speeds approaching the speed of light itself, time for the moving observer slows towards zero. The clock barely ticks at all. This is not a metaphor. It is not a description of how things seem to a confused observer. It is a description of what actually happens to time, to the physical process of duration itself, when an object moves fast enough. The twin paradox makes this viscerally concrete. Imagine two twins. One stays on Earth. The other boards a spacecraft, accelerates to a significant fraction of the speed of light, travels to a distant star, turns around, and comes back. When the traveling twin returns, the two of them stand face to face. They are no longer the same age. The twin who traveled, who experienced time passing more slowly because of the velocity of the spacecraft, has aged less, not metaphorically, not from the perspective of one observer versus another, physically, biologically. The cells in the traveling twin's body have divided fewer times. The neurons have fired fewer signals. The heart has beaten fewer beats. Time passed more slowly for one twin than for the other, and the difference is written into their bodies. This seems impossible. It offends every intuition we have about the nature of time and simultaneity and the shared reality of the universe. And yet, it is not only theoretically predicted, it is experimentally verified at the particle physics level every day. Subatomic particles called muons, created when cosmic rays strike the upper atmosphere, should decay in a fraction of a microsecond and never reach the Earth's surface. They do reach the surface. They reach it in enormous numbers. Because they are moving at close to the speed of light, time passes more slowly for them. And what is a fraction of a microsecond from our perspective is enough time for them to travel the full distance from the upper atmosphere to the ground. Moons are living, or rather decaying, proof of time dilation. They are the twin paradox happening in the atmosphere above your head continuously. Now, add gravity. General relativity, Einstein's 1915 theory, extends the picture of time dilation from velocity to gravity. A clock in a stronger gravitational field runs more slowly than a clock in a weaker one. Time passes more slowly closer to a massive object and more quickly further away from it. The difference on the surface of the Earth compared to a few kilometers above it is tiny. But it is real. And we know it is real because we depend on it working correctly every time we use GPS. The GPS satellites orbiting the Earth are moving fast, which causes their clocks to run slow by special relativity. And they are far from Earth's gravitational field, which causes their clocks to run fast by general relativity. The two effects do not cancel perfectly. The net result is that GPS satellite clocks run slightly fast compared to clocks on the ground. If the GPS system did not correct for this, if it simply assumed that time passes at the same rate in orbit as on the ground, the positioning errors would accumulate at roughly 11 kilometers per day. Within hours, the system would be useless. Every time GPS gives you an accurate location, it is doing so by accounting for the fact that time passes at different rates at different positions in a gravitational field. Einstein's general relativity is not a theoretical curiosity that physicists talk about at conferences. It is an engineering requirement built into the technology you use to navigate. Time is not universal. It is local. It is dependent on velocity and gravity in ways that are precisely calculable and practically consequential. Different points in the universe are experiencing different amounts of time right now, not different perceptions of time, not different measurements of a fixed underlying quantity, genuinely different amounts of a quantity that is not fixed and not universal and not independent of where you are and how fast you are moving. But here is where it gets stranger still. Relativity tells you that time is flexible. It stretches and compresses. It is not the same for everyone. These are deeply counterintuitive results, and they required a revolution in how physicists thought about space and time. But relativity does not tell you why time moves forward. Einstein's equations, both special and general, are time symmetric. If you take any solution to Einstein's field equations and reverse the direction of time, the result is also a valid solution. The mathematics does not prefer forward over backward. It does not contain any mechanism that makes time run in one direction rather than the other. And yet, time runs in one direction. Always, everywhere, without exception. Without a single documented case of time running backward in any physical system, at any scale, at any point in the history of the universe. You break an egg, and it does not reassemble. You mix cream into coffee, and it does not spontaneously separate. You watch a wave break on a shore, and it does not unbreak. These processes have a direction. They move from one state toward another and not back again. The universe has an arrow, a direction of travel, that is as robust and as universal as any physical law we know. And the fundamental equations of physics do not explain it. They allow it. They permit time-symmetric processes. But they do not demand the arrow. They do not contain within themselves the reason why the universe moves forward through time rather than backward, or why it does not move in both directions simultaneously, or why there is a direction at all. The explanation physicists offer, and it is a serious and well-developed explanation, not a placeholder, is thermodynamics. Specifically, the second law of thermodynamics and the concept of entropy. Entropy, roughly speaking, is a measure of disorder, the number of ways a system can be arranged while still having the same observable properties. A neatly stacked deck of cards has low entropy. There is essentially one arrangement that counts as a sorted deck. A shuffled deck has high entropy. There are millions of arrangements that count as a shuffled deck. The second law of thermodynamics states that in a closed system, entropy tends to increase over time. Things tend to become more disordered. The sorted deck, left to random shuffling, becomes unsorted. The hot coffee, left to cool, disperses its heat into the room. The wave, having broken, spreads its energy across the beach. The arrow of time in the thermodynamic picture is the arrow of increasing entropy. We remember the past and not the future because the past is the direction of lower entropy, the direction from which the highly ordered states that leave memories and records came. We cannot remember the future because the future is the direction of higher entropy, where those ordered states are dissolving. This is a compelling explanation. It is mathematically precise, and it captures something genuinely true about why time has an arrow. But it pushes the question back rather than answering it. Because if the laws of physics are time symmetric and entropy is what gives time its direction, then the universe must have started in an extremely low entropy state for entropy to have been increasing ever since. The Big Bang must have been extraordinarily ordered, a state of almost impossibly low entropy from which everything since has been a gradual dissolution into disorder. Why did the universe start in that state? The laws of physics do not say it had to. A high entropy beginning is just as consistent with the equations as a low entropy one. The specific initial condition that gave time its arrow, the extraordinarily improbable low entropy state of the early universe, is not explained by any physical law we currently possess. It is simply given, a fact about our universe that the laws describe but do not derive. The arrow of time is real. It is everywhere. It is the most universal asymmetry in nature, and its ultimate origin remains, at the level of fundamental physics, an open question, which is before we even arrive at the deepest problem, before we ask not why time moves in one direction, but whether it moves at all. The laws of physics are written in the language of mathematics. And mathematics, unlike human experience, has no preference for before or after. An equation describing the collision of two billiard balls works identically whether you run it forward or backward. A wave function evolving according to the Schrödinger equation, the fundamental equation of quantum mechanics, is equally valid in either temporal direction. The equations of electromagnetism, of gravity, of the strong and weak nuclear forces, every fundamental law of physics that we know, are symmetric under time reversal. Run the movie backward and the physics still works. This is not a minor technical detail. It is one of the most profound and underappreciated facts about the structure of reality. The universe, at its most fundamental mathematical level, does not know which direction time is supposed to go. The laws do not contain an arrow. They describe processes that are equally valid in both directions. And yet, everywhere you look, in every corner of the observable universe, at every scale from the subatomic to the cosmological, time moves in one direction and one direction only. How do you get a universal arrow from laws that contain no arrow? The thermodynamic answer we covered in the last section, entropy increases, and that increase defines the direction of time, is the best answer physics currently has. But as we noted, it pushes the problem back to the initial conditions of the universe rather than solving it. It explains why entropy increases now by pointing to the fact that entropy was extremely low at the beginning, without explaining why it was low at the beginning. Some physicists have pushed further. They have asked whether the thermodynamic explanation is really an explanation at all, or whether it is a sophisticated description of the phenomenon dressed up as a cause. Julian Barbour is one of the physicists who has pushed furthest. Barbour is a British physicist who has spent 50 years thinking about time with a rigor and persistence that has produced ideas considered genuinely radical even by the standards of a field accustomed to radical ideas. His central claim, developed across decades of work and published in his book, The End of Time, is that time does not exist. Not that time is weird. Not that time is relative. Not that time is complicated and we do not fully understand it. That time does not exist as a fundamental feature of reality. That what we experience as the passage of time is not the movement of a universe through a temporal dimension, but something more like the experience of a being embedded in a static structure, interpreting the correlations between different configurations of that structure as sequence. The universe, in Barbour's picture, is not a movie. It is a collection of frames. Each frame is a complete configuration of everything, every particle, every field, every quantum state, at what we would ordinarily call a moment in time. These frames exist, they are real, but they do not play. There is no projector, there is no real turning. The frames simply are an enormous, timeless collection of configurations related to each other by the laws of physics, but not animated by any flow. What we experience as time passing, the sensation of moving from one moment to the next, of the present becoming the past and the future becoming the present, is, in Barbour's view, the experience of a configuration that contains within it records and memories of other configurations. Each frame contains information about other frames. Each moment of experience is embedded in a configuration that encodes what we call the past. And consciousness, reading those encoded records, generates the experience of having moved through them. You are not traveling through time. You are a configuration that contains memories of earlier configurations and calls that sequence a journey. This is the block universe, or what Barbour calls Platonia. And it is not a fringe idea dismissed by mainstream physics. It is a serious philosophical and mathematical position that arises naturally from the time-symmetric structure of physical law and from particular approaches to the problem of quantum gravity. The block universe in its more standard form, without Barbour's specific elaborations, is actually the picture most consistent with special relativity. If time passes at different rates for different observers, if there is no universal present moment that everyone shares simultaneously, then the idea of a flowing now, a moving boundary between past and future that sweeps through the universe at the same rate for everyone, becomes difficult to sustain. Different observers have different nows. Their nows are related to each other by the geometry of spacetime, but they are not the same now. And if there is no universal now, then the flow of time, the movement of that universal present from past to future cannot be a fundamental feature of the universe as a whole. Einstein himself believed this. When his lifelong friend Michel Besso died in 1955, a few weeks before Einstein's own death, Einstein wrote to Besso's family with words that have become one of the most quoted statements any physicist has ever made about the nature of time. He wrote that Besso had departed this strange world a little before him, but that meant nothing. For those who believe in physics, the distinction between past, present, and future is only a stubbornly persistent illusion. A stubbornly persistent illusion from Albert Einstein, the man who more than anyone else transformed our understanding of time, who showed that it dilates, that it curves, that it is inseparable from space, who spent the last decades of his life working on a unified field theory that would bring quantum mechanics and general relativity together, who understood the mathematics of time more deeply than almost anyone who had ever lived. He thought the flowing present was an illusion. Carlo Rovelli, the Italian physicist whose books on quantum gravity and the nature of time have reached more general readers than almost any physics writing of the last decade, takes a position that is both similar and different. For Rovelli, time is real, but it is not fundamental. It is an emergent property, something that arises from the behavior of more fundamental things in the same way that temperature arises from the average behavior of molecules, or that wetness arises from the collective behavior of water molecules without any individual molecule being wet. In Rovelli's picture, developed from his work on loop quantum gravity, one of the leading approaches to unifying general relativity with quantum mechanics, the fundamental equations of quantum gravity do not contain time as a variable. The Wheeler-DeWitt equation, which is the central equation of canonical quantum gravity, famously does not include time. It describes the quantum state of the universe as a whole without any reference to when. Time, in Rovelli's view, emerges from this timeless description when you look at the correlations between subsystems of the universe. When one part of the universe serves as a clock for another part, and the relationship between them generates what we experience as temporal sequence. Time is not the background against which things happen. It is a way of describing the relationships between things that happen. Without those relationships, without the correlations between subsystems, time does not exist. What does it feel like to take this seriously? Not as an intellectual curiosity, not as an interesting thing to read about and then put down, but actually, seriously. To sit with the possibility that the most intimate feature of your existence, the one you cannot escape even for an instant, the one that carries you from birth toward death with a relentlessness that has defined every experience you have ever had, is not a fundamental feature of the universe, that it is emergent, that it is relational, that it is, in some deep sense, something the universe generates rather than something the universe is made of? Most people find this disturbing. Some people find it unexpectedly liberating. Because if the present moment is not a moving point on a fixed timeline, if past, present, and future are not stages in a sequence, but configurations in a structure, then the present moment is not disappearing as you experience it. It is not being lost. It is not receding into a past that no longer exists. It simply is. It exists as fully and as permanently as any other moment in the block universe. The configuration that contains your experience of right now is as real and as fixed and as permanent as any configuration that ever was or ever will be. Your existence is not temporary in the way it feels like it is. It is woven into the structure of what is. whether that structure involves time as a fundamental feature or generates it as an emergent one, whether the block universe is the right picture, or whether time is real but relational. The answer to the question of what time is remains, at the level of fundamental physics, genuinely open. And the places where it is most open, the places where time behaves most strangely, where our intuitions about it collapse most completely, are the extreme environments at the edges of the cosmos. The inside of a black hole, the moment of the Big Bang, the theoretical end of everything. Those are the places where the mystery of time shows its sharpest edges, and they are where we are going next. There is a place where time stops, not slows, not stretches in the way that velocity and gravity cause it to stretch in the experiments we have already covered. Stops completely. A boundary beyond which the question of what happens next becomes not difficult to answer, but meaningless to ask. That place is the event horizon of a black hole. To understand what happens to time at a black hole, you need to hold two perspectives simultaneously. The perspective of someone falling into the black hole and the perspective of someone watching from a safe distance outside. These two perspectives produce such radically different experiences of the same events that they seem, at first, to be describing entirely different physical situations. They are not. They are two valid descriptions of the same reality. And the fact that they are both valid simultaneously is one of the most unsettling things general relativity has ever produced. Start with the outside observer. You are watching from a safe distance. A clock, perfectly accurate, perfectly visible, is falling toward a black hole. As it falls, you watch it tick, and as it approaches the event horizon, the boundary beyond which nothing, not even light, can escape, you notice something. The clock is slowing down, not because anything is mechanically wrong with it, because time is passing more slowly for it as it descends deeper into the black hole's gravitational field. General relativity predicts this with precise mathematical specificity. The stronger the gravitational field, the slower time passes. And a black hole's gravitational field increases without limit as you approach the singularity at its center. As the clock approaches the event horizon, the slowing becomes more and more extreme. The ticks come further and further apart. The hands of the clock, if it had hands, move more and more slowly. And at the event horizon itself, from your perspective as the outside observer, the clock stops completely. The last tick before the horizon is the last tick you ever see. The clock does not cross the horizon from your perspective. It hangs there, frozen at the boundary, the final moment of its approach stretched into an infinite stillness. Its image redshifts. The light it emits shifts to longer and longer wavelengths as the gravitational field stretches it, and eventually fades beyond detectability. But in principle, in the pure mathematics of general relativity, that frozen image persists forever. The clock is suspended at the horizon for the rest of the universe's history, from the perspective of any external observer. Time for the infalling clock has stopped. Now take the perspective of the clock itself. From inside the falling reference frame, nothing unusual happens at the event horizon. The clock ticks normally. The person riding alongside it feels no dramatic physical sensation as the horizon is crossed. No wall, no barrier, no indication that anything special has occurred. The equations of general relativity predict that for a sufficiently large black hole, the curvature of spacetime at the event horizon is gentle enough that a freely falling observer would not notice the crossing at all. They cross the horizon, they continue falling, they have time, from their own perspective, to think, to observe, to record measurements. Time for them continues to pass in its familiar way, but they cannot communicate this to the outside observer. Any signal they send after crossing the horizon, any light, any radio wave, any information of any kind, cannot escape the black hole's gravity. It falls inward along with everything else. The outside observer never receives it. From the outside, the infalling observer is frozen at the horizon forever. From the inside, the infalling observer crosses the horizon and continues falling toward the singularity at the center. Both of these descriptions are correct. They are not contradictions. They are two different but equally valid perspectives on a region of spacetime so extreme that our familiar intuitions about simultaneity and shared experience and the objective passage of time break down completely. And what they tell you together is this: time is not a thing that exists independently of the physical situation of the observer. It is not a river flowing at the same rate through every region of space. It is a dimension. And like spatial dimensions, it can be curved, compressed, stretched, and in the vicinity of a black hole's event horizon, effectively frozen for one observer while continuing normally for another. The singularity at the center of the black hole is worse. At the singularity, the point at the center toward which everything that crosses the event horizon inevitably falls, the curvature of space-time becomes infinite. The equations of general relativity, which have been so extraordinarily successful at describing everything from the orbit of Mercury to the detection of gravitational waves, produce a result at the singularity that physicists have a technical term for. They break down. The mathematical description of spacetime at a singularity produces infinities, values that have no physical meaning, outputs that tell you nothing about what is actually happening, because the framework within which the calculation is being made has ceased to be applicable. The equations stop working. And when the equations stop working at a singularity, one of the things that stops working with them is time. What happens to time at a singularity is genuinely unknown. Not unknown in the sense of being unmeasured, unknown in the sense of being theoretically undefined. The framework within which time is described, general relativity, does not extend to the singularity. And the framework that would replace it, quantum gravity in whatever form it eventually takes, does not yet exist in complete enough form to answer the question. The singularity at the center of a black hole is a place where our understanding of time runs out entirely, not because we have not looked carefully enough, because the mathematics itself tells us it cannot reach there. Now go further back. Before black holes, before stars, before galaxies, before any structure in the universe existed at all. Go back to the Big Bang. The Big Bang is not an explosion in space. This is perhaps the most common misconception about cosmology, and it is worth correcting clearly. The Big Bang is not something that happened at a specific location within a pre-existing space. A detonation at some central point from which everything expanded outward into emptiness. There was no pre-existing space for it to happen in. The Big Bang is the origin of space itself. And along with space, inseparably according to general relativity, which binds space and time into a single four-dimensional fabric, it is the origin of time. Before the Big Bang, there was not a time when nothing existed. There was no before. The question of what came before the Big Bang is not a question that awaits a difficult answer. It is a question that may not be well formed. Time, as general relativity describes it, began with the Big Bang. Asking what happened before time began is like asking what is south of the South Pole. The direction you are pointing does not exist beyond the boundary you are asking about. Stephen Hawking and James Hartle developed a model, the no boundary proposal, in which the universe has no boundary in time any more than the Earth has a boundary in space. The South Pole is a point on the Earth's surface, not an edge beyond which something else begins. In the Hartle-Hawking proposal, the beginning of the universe is a point in a four-dimensional structure, not a moment in time beyond which there was an earlier time that physics has not yet described, but a boundary in the mathematical sense, a point at which the dimension of time smoothly becomes indistinguishable from a spatial dimension, and the concept of earlier loses its meaning. This is deeply strange. It requires holding in your mind a picture of a universe that is finite in time, but has no beginning, no first moment, in the same way that the Earth is finite in space, but has no edge. And it requires accepting that the intuitions about time that evolution has built into every human mind, the intuitions that say, of course there was a before, of course something preceded this moment, maybe intuitions about a local feature of our experience that do not generalize to the universe as a whole. Time, as we experience it, is a local phenomenon, and locally it feels infinite in both directions. The past recedes as far back as we care to look. The future extends as far forward as we care to imagine. But the universe is not required to match our local experience, and the evidence, the mathematics of general relativity taken seriously, the physics of the Big Bang followed to its logical conclusion, suggests that the universe does not match our local experience. Time began, possibly, in some sense that we do not yet fully understand and may never fully understand with the theories we currently have. And at the other end, at the theoretical end of everything, time faces a different kind of strangeness. The universe is expanding, not just expanding, but accelerating in its expansion. Driven by dark energy, the mysterious component of the universe, whose nature remains one of the deepest unsolved problems in cosmology. If that acceleration continues indefinitely, and the current evidence suggests it will, the distant future of the universe is one of increasing isolation. Galaxies moving beyond each other's cosmological horizons, stars burning out one by one across trillions of years, black holes evaporating through Hawking radiation across timescales so vast that the number of years required to express them has more digits than there are atoms in the observable universe. And eventually, after a duration so long that the word eventually feels almost comically inadequate, a state that physicists call the heat death of the universe. Maximum entropy, thermodynamic equilibrium, a universe in which no structure remains that could serve as a clock, no temperature gradient that could drive any process, no information flowing from one place to another in any way that could mark the passage of time. A universe in which time, in any meaningful sense, has ceased to exist, not because time has ended in the way it began, not because of a singularity or a boundary in the mathematical sense, but because time, if it is fundamentally about the correlations between physical systems and the flow of information between subsystems of the universe, has nothing left to be about. The correlations are gone. The information has dissolved into maximum disorder. The universe sits in a state that is as close to timeless as a physical system can get without invoking quantum gravity. Time, at its extremes, disappears. At the singularity, at the Big Bang, at the heat death. In every direction, you push the question far enough. Time, the thing you cannot stop, the thing you have never been outside of, the thing that feels like the most real and fundamental feature of existence, begins to dissolve. And if it dissolves at the extremes, the question becomes unavoidable. Was it ever really there? Or was it always something the universe was generating, locally, contingently, for the benefit of observers embedded within it, rather than something the universe fundamentally is? That question has no settled answer. But the people who have thought about it most carefully, who have followed the mathematics wherever it leads, and tried to construct a theory of reality complete enough to answer it, have arrived at positions that share a common feature. They all suggest that time, as we experience it, is not the deepest thing. That underneath the river of moments, there is something else. Something that the river flows through, or something from which the river emerges, or something of which the river is a local approximation that works beautifully within the range of our experience and breaks down at the edges. What that something is, physics is still working out, and the working out is happening now. In papers and in conversations and in mathematics being written on whiteboards in universities and research institutes around the world. In the quiet, persistent, unglamorous work of people trying to build a theory of quantum gravity that would finally tell us what time is at its most fundamental level. We are not there yet, but we are asking the right questions. And asking the right questions in science is how you eventually find the right answers. There is a question that children ask and that adults learn to stop asking. Not because the question gets answered, because it becomes socially uncomfortable to keep asking it. Because at some point, the people around you signal through tone and expression and the gentle redirection of conversation that this is a question you are supposed to have made peace with rather than continued to pursue. The question is this: what is time for? Not what is time made of, not how does it work, not where did it come from. Those are the questions physics is working on and making progress with, however slowly and incompletely. But the deeper one, the one that sits underneath all the physics, the one that the physics does not address because it is not the kind of question physics knows how to answer. Why does time exist at all? Why should there be a universe in which things happen sequentially rather than simultaneously? Why should there be a dimension in which causes precede effects, in which memory points one way and anticipation points another, in which experience accumulates rather than simply being? Why should there be, as the philosopher David Albert has put it, a difference between the way things are and the way things were? The universe did not have to work this way. A timeless universe is physically conceivable. A universe in which the block of space-time simply exists, all of it, all at once, without any dimension that privileges sequence over simultaneity, is not ruled out by any logical principle. It is simply not the universe we find ourselves in. Or rather, it is possibly exactly the universe we find ourselves in, and the sequence we experience is a feature of our particular position within the block rather than a feature of the block itself. This is the point at which physics and philosophy become genuinely difficult to separate. Because the question of whether time is fundamental or emergent, whether the flow is real or illusory, whether the Present moment is a moving boundary or a fixed point in a static structure. These questions cannot be answered purely by experiment. They require not just data, but interpretation, not just measurement, but understanding. And understanding at this level requires engaging with questions that physicists and philosophers have been arguing about for centuries without resolution. Carlo Rovelli, whose writing about time is some of the most beautiful and honest in contemporary physics, has a way of framing this that I find more clarifying than almost anything else in the literature on the subject. He says that time is the form of our ignorance. What he means by this is specific and worth unpacking carefully. In classical physics, the physics of Newton, the physics of everyday intuition, the state of the universe at any given moment is in principle completely determined. If you knew the position and velocity of every particle in the universe at one instant, you could calculate the complete future and complete past of every particle forever. There would be no uncertainty, no ignorance. The universe would be a machine whose state at one moment determined its state at every other moment. In such a universe, time would still exist as a dimension, as the variable in which those states succeed each other. But the distinction between past, present, and future would be merely practical, not fundamental. The future would be as determined and as knowable as the past, in principle. The arrow of time would be a feature of the complexity of the system and our limited computational capacity to analyze it, not a fundamental asymmetry in nature. Now add quantum mechanics. Quantum mechanics introduces genuine, irreducible uncertainty into the description of physical systems. The state of a quantum system is not a precise point in phase space, but a probability distribution, a superposition of possible states that collapses, in some interpretations, only when a measurement is made. The future is not determined by the present in any strong sense. There are genuinely open possibilities at every moment that are closed or opened by what happens. And here, Ravelli's insight becomes sharpest. If the future is genuinely open, if what happens next is not fully determined by what has happened, then time is the dimension in which that openness resolves. Time is where possibility becomes actuality, where the superposition of what might happen collapses into what does happen, where the universe, in a sense, makes up its mind. Time, in this picture, is not a pre-existing container in which events occur. It is the process by which the indeterminate becomes determinate. The mechanism, if you can call it that, by which a universe that could have been otherwise becomes the specific universe that is. This is why Ravelli says time is the form of our ignorance, not because time is unreal or illusory. He is not making that claim, but because time is the dimension that exists because the future is not known, because there is something left to happen, because the universe has not yet finished becoming what it will be. In a universe of complete determinism, in which everything that ever happens is already implicit in the initial conditions, time is merely a parameter, a label attached to each point in the block. In a universe of genuine quantum indeterminacy, time is something more. It is the space in which the universe exercises whatever it exercises that we choose to call becoming. Whether that is the right picture, whether quantum mechanics really introduces genuine openness, or whether the apparent indeterminacy is simply our ignorance of a deeper deterministic structure, is itself one of the deepest unsolved questions in physics. Different interpretations of quantum mechanics give different answers. The Copenhagen interpretation says the wave function collapse is real and the future is genuinely open. The many worlds interpretation says all possibilities are realized in branching universes. And what we experience as collapse is simply our trajectory through one branch among many. Pilot wave theories say there is a deeper deterministic reality beneath the quantum uncertainty. Each interpretation has implications for what time is, and none of them is universally accepted. What you are left with, if you follow this carefully and honestly, is not a clean answer. It is a landscape of serious, mathematically developed positions that disagree with each other in ways that have not yet been resolved, that may require experimental evidence we do not yet know how to obtain, or theoretical insight we have not yet had before they can be resolved. Time is real, in the sense that the universe has a structure in which things succeed each other and in which past and future are genuinely different. Time is relative, in the sense that the rate at which it passes depends on velocity and gravity in precisely measurable ways. Time may be emergent in the sense that the most fundamental equations of quantum gravity do not contain it, and it arises from the relationships between physical systems rather than being built into the bedrock of reality. Time may be illusory in the sense that the flow, the moving present, the sense of moments passing, may be a feature of consciousness rather than a feature of the universe. All of these things can be simultaneously true in different senses of true. And sitting with that, sitting with the recognition that the most intimate and unavoidable feature of your existence is also one of the least understood features of the universe, is not a comfortable place to be. But it is an honest one. And honesty, in this case, is more valuable than comfort. Because the alternative, the pretense that time is well understood, that we know what it is and where it comes from and why it moves in the direction it does, is a pretense that closes off the very questions whose answers might, eventually, tell us something about reality that we cannot currently imagine. The deepest things we do not understand are not obstacles to knowledge. They are the frontiers of it. There is something worth saying before we close, something that is not physics and not philosophy, but sits in the space between them, where the question of what time is connects to the question of what it means to exist inside it. You are right now at a specific point in time, not in the casual sense, in the precise sense. This moment, the configuration of the universe that contains your experience of listening to these words in this order at this pace, is a specific point in the four-dimensional structure of spacetime. It has coordinates. It has a precise relationship to every other moment that has ever occurred or will ever occur. And if the block universe picture is correct, if past, present, and future all exist with equal reality in a static four-dimensional structure, then this moment is permanent. Not permanent in the sense of lasting forever in the future. Permanent in the sense of simply existing, fixed, unchangeable, as real as anything that physics can describe, at its specific location in the block. The present moment you are experiencing right now will never stop having happened. Whatever the physics of time turns out to be, whether time is fundamental or emergent, whether the flow is real or generated by consciousness, whether the arrow is explained by entropy or by something deeper that we have not yet found, the configuration of the universe that contains this experience is woven into what exists. That is not nothing. In a universe where time is a mystery, where the most rigorous thinkers who have engaged with the question have arrived at conclusions ranging from time is relative to time is emergent to time does not exist at the most fundamental level. There is something clarifying about this. The mystery does not diminish the moment. If anything, it intensifies it. Because a moment that is genuinely mysterious, whose relationship to the fabric of reality is not fully understood, that sits at the intersection of quantum mechanics and general relativity and consciousness and thermodynamics in ways that no current theory can completely describe, is not a less real moment for being mysterious. It is perhaps a more interesting one. You are alive inside one of the deepest unsolved problems in physics, not as a metaphor, not as a poetic flourish, literally. The question of what time is, what the dimension you are currently moving through actually is at its most fundamental level, is an open question in the most rigorous scientific sense of the term. The people who have dedicated their careers to answering it have not yet answered it. The experiments that would resolve the deepest disagreements have not yet been designed. The theory that would unify general relativity and quantum mechanics, and in doing so would likely tell us what time is and where it comes from, has not yet been written. You are inside a mystery that the best minds of this generation are working to solve. And the fact that they have not yet solved it is not a reason for despair. It is a reason to keep asking. The universe has been here for 13.8 billion years. It has produced stars and galaxies and planets and oceans and life and consciousness and language and mathematics and physics. It has produced creatures capable of standing on one of its planets and asking, with genuine rigor and genuine humility, what the dimension they are embedded in actually is. We are those creatures. We are the universe asking about time from inside time. And if that is not worth staying awake a little longer to think about, if that is not worth one more quiet moment before sleep, then I am not sure what is. If this changed the way you see time, the thing you cannot stop, the thing you have never been outside of, the thing that remains one of the deepest mysteries in all of physics. The cosmic depth has more waiting for you. Subscribe, and I will see you in the next one.